Hi there, my name is Kaylee, and this video is solving problems with energy equations with friction. And this is the last video in the mechanical energy unit, so make sure you've watched the previous videos already, and especially the equations for friction and thermal energy. So in this video, we're going to be working through problems as they would happen in the real world where friction is present. So it's really exciting. We'll see how far a biker coasts after they stop pedaling on a ground that has friction and things like that. So it'll be really exciting. So quick review. Just going to go over our energy equations, remembering kinetic energy is 1/2 mv squared. Potential energy is mgh. The equation for friction is mu times the normal force. And thermal energy is friction times the distance traveled over a surface with friction. And as always, E total is going to equal all of the energies added together. And along the same line, conservation of energy. Energy is never created or destroyed, and so the total energy must always be the same. All right, so as we work through these problems, it'll be helpful for you to have these equations to refer to. So if you want to write them down or pause the video and go back and check them at any time, I would recommend that. All right, let's get started. All right, next question. A block is sliding down a 3-meter long ramp. If the force of friction on the block is 18 newtons, what is the thermal energy of the block at the bottom of the ramp? Okay, let's think about this here. Let's write down what we know for sure. I know for sure that the force of friction on the block is 18 newtons. So let's write that down. We know little f is equal to 18 newtons. Okay. And then they're asking us, what is the thermal energy of the block at the bottom of the ramp? So at the bottom, if it's at the bottom of the ramp, how far has it slid? 3-meter long ramp. So it's slid over a distance of 3 meters. Okay. So I'm going to say D here is 3 meters. And they're saying, what is the thermal energy? Thermal energy. We have that equation. Ready? So E sub T is equal to the force of friction times the distance the object slides while experiencing that friction. Here we go. The object is the block. The block is experiencing friction of 18 newtons, and it's sliding over a 3-meter long ramp. So let's plug those in there. So force of friction is 18 newtons. The distance it's going to travel is 3 meters. Okay, before we do this calculation, let's make sure that this makes sense. So thermal energy here, I'm looking for a number that has a unit of joules. So I'm looking for energy. And I'm multiplying a force by distance. So I'm multiplying a newton by a meter. And as we remember, a newton meter is equal to a joule. So good, we should be in business here. So if I plug this into my calculator, 18 newtons times 3 meters is going to be 54 joules. Alrighty here. So we can write ET, the thermal energy at the bottom of the ramp is going to be 54 joules. Nice, let's put a little square around that. Boxing up our answer. So a block with a force of friction of 18 newtons slides down 3 meters. It will have a thermal energy of 54 joules. Nice job. All right, so now we're going to go on to a more complicated question here. And it goes, a biker on a smooth road begins coasting on a rough road at 6 meters per second. The biker and the bike are 72 kilograms with a normal force of 684 newtons. The rough road has a coefficient of friction of 0.6. How far has the biker coasted before coming to a stop due to friction? All right. So first things first, that's a lot of information. Let's just write down what we know. So we know that the bike and the biker have a mass of 72 kilograms. So M is equal to 72 kilograms. And have a normal force of 684 newtons. So normal force Fn is equal to 684 newtons. The rough road has a coefficient of friction of 0.6. Remember, coefficient of friction, unitless, is our fancy friend mu. It's equal to 0.6. And when she begins coasting, she has a speed of 6 meters per second. Okay, so V is equal to 6 meters per second. Remember this V, I'm going to call it V1 because it's the beginning. The number one speed she has is 6 meters per second, the start. And how far has the biker coasted before coming to a stop due to friction? So a stop, so that means her V2, her V at the end, her second velocity is 0 meters per second. Okay. So now let's investigate this. What are they asking us? So the question starts here. How far has the biker coasted before coming to a stop? So how far, that here makes me think distance. So what we're looking for is D, or distance. And that means we're looking for something in meters, right? So we're looking for something in meters, a number with meters. So how far has the biker coasted before coming to a stop due to friction? So this is important. Due to friction, we do have an equation that has a D in it, right? So it goes ET is equal to the friction force times D. So we're looking for this D here. Do we know what this friction force is? I don't think we have that number, but we do know that, remember, little f friction is equal to mu Fn. And I do believe we have a mu, 0.6, and we have an Fn, 684 newtons. Okay, so first things first, let's just figure out this. So this is going to be equal to 0.6, and Fn is 684 newtons. And this I'm going to plug into my calculator. And that comes out to 410.4 newtons. Okay, so let's just put this little f over here too. So now we have friction force is 410.4 newtons. Okay, so now what we want to know, let's rewrite this. ET is equal to FD. So we want to know what this D is. So let's get it all by itself. Let's divide both sides by little f. So now we have these cancel out. We have D is equal to thermal energy over the force of friction. Okay, great. So now we need to know what ET is. So we need to know what's that actual thermal energy equal to. So let's go back to our question here. A biker on a smooth road begins coasting on a rough road at 6 meters per second. So right at the beginning, she's on a smooth road and she has a velocity of 6 meters per second. And nowhere in here does it say anything about a hill or being high off the ground. So we can assume right now that at the beginning on this smooth road without friction, the biker only has kinetic energy. Okay? And at the end, the biker has coasted to a stop. So at the end, remember we know that V2 over here is 0 meters per second. We still know she's not on a hill. She's no height off the ground, so there's no potential energy. So let's think about our COE, our conservation of energy, means E total equals E total, always the same. So for us, we can say E1 at the beginning is going to equal E2. And if at the beginning all she has is kinetic energy, so E1 is going to be EK, is that kinetic energy is equal to that thermal energy because she only has frictional energy now at the end. Okay, so we have this ET, and we need it because we need to know what this D is. Okay, so EK at the beginning, we can figure that out. So EK is equal to 1/2 mv squared, and this is V1 at the beginning, remember. And that is going to be equal to 1/2. The mass of the biker and the bike, remember, is 72 kilograms, and it was 6 meters per second squared. All right, looks like we're running out of space here, so let's go down to a fresh page. We can come back up to here to get our numbers as we need them. All right, so here we are with a fresh page. I'm just going to rewrite our EK is equal to 1/2 the mass, 72 kilograms, times 6 meters per second squared. All right, so let's do the math here. We say 1/2 72 kilograms times squaring our number and our units, 36 meters squared over seconds squared. And the rest of this here, I'm just going to plug into my calculator. So that comes out to be 1,296. Remember, a kilogram times a meter squared times a second squared. So kilogram meter squared over second squared is equal to 1,296 joules. Okay, so remember, EK is equal to E1, which is equal to E2, which is equal to ET. And remember, we need ET because we need that D. Okay, we need to know that distance. That's what they're asking us. How far? What's the distance here? Okay, so now we know EK equals ET equals 1,296 joules. Okay, so that's our initial energy. Then ET is our final energy. And we know that it's the only energy because that V2 is equal to 0. So that means kinetic energy is equal to 0 at the end. We know there's no potential energy. They never give us a height or anything off the ground. Okay, so now remember, ET is equal to FD. We divided both these sides by F. And we got D is equal to ET over F. So now we know ET, 1,296 joules divided by, remember we calculated this friction force because we knew mu and we knew Fn, and we got 410.4 newtons. Okay, remember what we're looking for here is D, which is meters. Remember we said we're looking for distance, and distance is a meter. So let's check our units right now. We have a joule divided by a newton. So what is a joule divided by a newton? So if we remember, a joule is equal to a newton meter. So if we were to divide both sides by newton, we would end up with meters. So perfect, we're jamming here. We just plug this into our calculator and we get 3.16 joules per newton, which is equal to 3.16 meters. Awesome. So D is equal to 3.16 meters. That was a lot of work. Great job. So now let's think about, conceptualize what this means. So the distance, how far has the biker coasted before coming to a stop due to friction? So the distance that the biker will have traveled is 3.16 meters before coming to a stop due to friction, when she started with a kinetic energy and a speed of 6 meters per second. Amazing work. That was a lot. So I would go back and review this one more time and see how we made those connections between conservation of energy and what friction does to our velocity, and how having our velocity go to zero means that all of our energy went to thermal energy. So nice work. So this concludes our unit on mechanical energy in physics. Make sure you play the games solving energy problems with friction and the one without friction as well, so you can practice on your own. Great job, and remember to always be clever. Hey, hey.